The crane truck equipped with the HIABX Hipro 408E6 and Jib 70X4 offers a highly efficient solution for tree sawing and heavy lifting operations. This combination provides exceptional reach and lifting capacity, making it ideal for forestry and transport tasks. The HIABX Hipro 408E6 crane features advanced hydraulic technology with 6 extension sections, enabling smooth and precise control over load positioning. The attached Jib 70X4 extends operational versatility by increasing outreach and access to difficult-to-reach areas, critical in tree cutting and removal operations. Together, the crane and jib deliver high torque and stable lifting performance, even under challenging conditions. The crane truck's robust build, combined with state-of-the-art control systems, ensures safe and reliable operation on site. Janssen and Frank Transport employs this equipment to optimize workflow, reduce manual labor, and improve overall project efficiency during tree sawing and transport logistics. The integration of the HIAB crane system maximizes load handling and maneuverability, crucial for forestry industry applications. The production of Lux door interior and exterior doors follows a technologically integrated workflow that ensures structural strength, aesthetic quality, and precision in all assembly phases. The process incorporates CNC machining, multi-stage finishing, and the integration of decorative and functional glass elements. Manufacturing begins with the selection and moisture calibration of raw materials such as engineered wood, MDF, or solid wood. These substrates are cut into stiles, rails, and panels using automated saws and CNC routers based on CAD specifications. Frame components are assembled using dowel or mortise and tenon joints, with adhesive application under high-pressure presses to ensure rigidity. Surface preparation includes mechanical sanding and defect correction. For laminated or veneered doors, decorative surfaces, corporal, PVC foil, or natural veneer are applied using hot pressing under controlled temperature and pressure. Solid wood variants receive multiple layers of stain and UV-cured lacquer in a dust-free coating booth. In door models featuring glass inserts, precision CNC cutting of glass sheets is performed according to the door design. Glass types may include clear, frosted, tinted, or laminated safety glass. Decorative processes, such as sandblasting, acid etching, screen printing, or laser engraving, are applied to create patterned or frosted designs, depending on the model. Once prepared, glass panels are securely mounted into milled apertures in the door leaf using gaskets, clips, or structural adhesives, ensuring vibration resistance and sealing integrity. Edge protectors and glazing beads are added if required by the design. Additional machining for lock sets, hinges, and handle preparation is carried out using dedicated boring and milling units. Final inspection checks dimensional accuracy, finish quality, glass integrity, and mechanical stability. The finished doors are then packaged using shock-absorbing materials, ensuring safe transport while maintaining the Lux door standard of design, durability, and performance. In the Malay boat-building village depicted in Maurizio Borriello's documentary, traditional wooden boat building emerges not merely as a means of production, but as a cohesive system of tacit knowledge transmission, collective labor, and deep environmental literacy. The process begins with site selection, an intergenerationally inherited boatyard typically located along the mangrove-lined rivers or coastal areas of Malaysia, where proximity to tidal waters, access to specific species of hardwood, and seasonal weather patterns dictate work feasibility. Boat builders operate without formal plans. Instead, the boat's proportions and geometry are embedded in the memory of senior builders, usually the master shipwright, who acts as both project lead and oral archive. The construction process starts with the keel, carved from a single massive hardwood trunk, typically Chengal, Neobalanocarpus hemii, prized for its high density, resistance to marine borers, and natural oils that deter decay. Sourcing such a trunk involves logging in inland forests, using chainsaws to fell and rough shape it before river floating it downstream to the coastal yards. The keel is then carefully laid on a bedding of stone and timber, with constant alignment checks using plumb lines and rudimentary levels to ensure symmetrical elevation. Unlike Western methods that use molds or frames first, Malay boat building follows a shell-first construction. The hull planks are edge-fastened and shaped without the use of frames or ribs initially. Each plank is fire-bent on-site using a long trough of burning coals and damp cloths to soften the wood fibers. Bending requires skillful judgment of temperature and timing, executed through team coordination rather than instrumentation. The softened planks are pressed into the growing hull and held in place using temporary wooden clamps, nails, and thick iron spikes, traditionally hand-forged. The seams between the planks are sealed with a caulking mixture of cotton fibers soaked in damar resin, sourced from native trees, combined with animal fats to enhance pliability and longevity. This mixture is tamped into the seams with chisels and wooden hammers, followed by a final resin layer brushed externally to waterproof the hull.
Barang zaman dulu. Zaman orang tua. Modern. Masih bagus. Modern dulu. Tekan turun. Balik atas pula.
Once the shell reaches a designated height, internal structural components are installed. The transverse frames, made of hardwood branches bent naturally into rib-like curves, are inserted inside the shell and affixed with wooden tree nails and iron fasteners. Deck beams, thwarts, and transoms are progressively fitted. The final hull is characterized by a deep V form and high prow, optimized for choppy coastal waters and efficient cargo loading. This symmetrical shaping is achieved not through CAD tools, but through decades of embodied calibration by eye, hand, and oral cues, a dynamic system where geometry is embodied rather than diagrammed. Tool usage remains consistent with earlier periods. Adzes, draught knives, handsaws, and augers dominate. Despite the presence of chainsaws for rough cuts, precision shaping is manual, conducted on dirt floors with timber propped on makeshift trestles. The adze is used not only for carving, but also for planing and beveling joinery surfaces. Measurements are rarely taken using metric tapes. Instead, builders use their palms, arms, or known distances like a master's stride to gauge length and proportion. Boats range from small fishing pirohu to 20-meter cargo vessels, all built under open-air canopies fashioned from bamboo poles and palm thatch. This open environment allows ventilation for both the craftsmen and the drying timbers. Boat builders work barefoot for tactile feedback and are continuously assessing wood quality through sound, tapping for resonance, scent for rot detection, and grain behavior for optimal cut direction. Waste wood is repurposed for scaffolding, firewood for bending, or tool handles, maximizing resource efficiency.
Dia kemban air tidak dapat masuk. Masuk dengan sikit-sikit. Dia
The entire building process may take 4 to 8 months, depending on vessel size, timber availability, and weather. Tidal cycles influence daily schedules. High tide is essential for launching, while low tide exposes keel lines for inspection. Communication is verbal and rhythmic. Hammer strokes, chants, and calls synchronize group actions, particularly during lifting, bending, and caulking phases. Once construction nears completion, elaborate rituals often accompany the launch, reaffirming the boat's integration into both material and spiritual domains. A coconut may be broken on the bow, prayers offered, and symbolic objects embedded within the keelson for protection. The launch itself is timed to lunar phases and tide cycles, and may involve the entire village in collective effort. Final finishing includes oiling the hull with a mixture of coconut oil and additional damar resin to reduce marine fouling and enhance sheen. Maintenance is integral to the craft. Every 12 to 18 months, boats return to the yard for inspection, hull scraping, caulking repairs, and reapplication of protective coatings. This cyclical engagement ensures longevity, with some vessels operating for 25 to 30 years. During maintenance, younger apprentices observe and gradually perform more tasks under the guidance of senior builders, thus perpetuating the transfer of skills in an informal yet deeply structured pedagogical system. Borriello's film emphasizes that Malay boat building is not an isolated craft, but a complex socio-technical system. It involves ecological knowledge, tree species, forest cycles, resin behavior, material science, bending thresholds, decay resistance, geometry, hull design, displacement curves, and cultural protocols, ritual, apprenticeship, oral codes. The process exemplifies a vernacular technology rooted in place-based intelligence, optimized over generations not through formal design, but through continuous feedback from sea conditions, material behavior, and operational experience. Technically, the approach reflects a pre-industrial, low-entropy model of manufacturing. Energy inputs are primarily human and thermal, firewood, with minimal fossil fuel dependency. Waste is almost non-existent, and life cycle thinking, from timber harvesting to decommissioning, is embedded in practice. Each vessel is a bespoke response to a specific set of needs, rather than a standardized product, highlighting adaptability and resilience. In the face of industrialization and fiberglass proliferation, this form of wooden boat building faces decline. Yet, as Borriello captures, it offers a repository of embodied knowledge that remains technically sophisticated, environmentally integrated, and culturally irreplaceable. The challenge lies not in modernizing it, but in understanding its systemic coherence and fostering conditions for its continuity, possibly through hybridization, digital documentation, and artisan support programs. The whole mold construction begins with the completion of the plug frame, which is built using wood to outline the full-scale shape of the hull. This skeleton-like structure defines the outer contours of the final boat. Once the frame is ready, long, narrow planks are carefully attached along the frame's curvature. This planking process forms a smooth, continuous surface that resembles the shape of the actual hull. After planking is complete, the first phase of sanding begins. Workers use electric sanders and hand tools to smooth the surface, eliminating rough edges and imperfections. Once sanded, a layer of primer is evenly sprayed across the entire surface. This primer seals the wood and prepares it for the fiberglass application. The fiberglass process starts by laying down multiple layers of fiberglass cloth, which are then saturated with resin. This creates a hard, durable shell over the plug. After curing, another round of sanding is performed to ensure a flawless surface. Primer is applied again, followed by a second round of fiberglass lamination to strengthen the mold. Next, internal structural supports, such as foam cores and stringers, are bonded onto the backside of the fiberglass mold. These components give the mold rigidity, allowing it to retain its shape under stress. Once all layers and reinforcements are cured and secured, the entire mold is carefully flipped over using cranes or lifting equipment. This flipping process exposes the interior surface of the mold, which will later be used to fabricate fiberglass boat hulls. The 3D printing process of the marine boat hull pattern using LSAM system starts by printing large polymer beads at room temperature onto a patented beadboard. The compression wheel flattens and fuses each new bead with the previous layer, ensuring strong bonding through controlled cooling. As the polymer cools within a precise temperature range, layers are continuously added to form individual sections of the hull. Once printed, the sections are carefully removed and joined together to form the complete hull pattern. The assembled structure is then machined on the same LSAM system for dimensional accuracy and smooth surface finish. After machining, the pattern undergoes final trimming to remove excess material. The finished, trimmed pattern is then ready for coating and mold production. The micromill is used to perform highly precise and complex cuts during the construction of log homes. The cutting process begins by securely positioning the logs on a stable support structure. Operators ensure the log is properly aligned and firmly clamped to prevent any movement during cutting, which is essential for maintaining high precision. The setup phase includes measuring the log dimensions and verifying that it fits the required specifications for the planned notches and joints. Next, the operator selects the specific cutting program tailored to the log house design. The micromill's control panel allows input of detailed parameters, such as cutting depth, angle, length, and shape, depending on the type of cut needed, whether for corner notches, saddle cuts, or complex joint profiles. The program can be adjusted to accommodate different wood species and thicknesses. Once the parameters are set, the micromill's cutting head is activated. The tool rotates at high speed, smoothly slicing through the wood fiber with minimal resistance. The machine operates on multiple axes, enabling it to perform not only straight cuts, but also precise angled and contoured cuts required for perfect log fitting. The high rigidity of the machine structure reduces vibration, which improves the surface finish and cutting accuracy. Throughout the cutting operation, sensors and the control system continuously monitor the tool path and adjust movements to ensure exact adherence to the program dimensions. This feedback loop prevents deviations and guarantees that each cut matches the design specifications perfectly. After completing one cut, the log is unclamped and repositioned or replaced with the next piece, continuing the workflow. The micro mill enables rapid, repeatable precision cutting, reducing manual rework and speeding up the entire log house assembly process. By using the micromill, operators achieve clean, tight-fitting joints that are essential for the structural integrity and insulation of the blockhouse, all performed with ease and high reliability. The production of the new €50 banknote is a highly secure and technically sophisticated process, involving a blend of traditional paper-making and advanced printing technologies. The journey begins with the warehousing and stacking of cotton bales, the raw material used in the production of banknote paper. Cotton is preferred over wood pulp due to its superior durability and resistance to wear. Once staged, the cotton bales are separated and cut into smaller pieces to facilitate further processing. The cut cotton is then transported into pulping vats, where it undergoes a mixing process to form paper pulp. This pulp is cleaned, refined, and mixed with synthetic fibers and special additives to enhance the security and printing properties of the final product. As the pulp is spread into sheets and pressed, a watermark is integrated into the still wet paper through pressure and variation in fiber density, forming one of the key security features. These finished paper sheets, still in large rolls known as mother reels, are dried and inspected. A special transparent window is also embedded during the paper-making phase in newer banknote designs, allowing for the inclusion of embedded holographic elements. Once the paper is finalized, automatic cutting machines divide the mother reels into 3 smaller reels for easier handling in downstream printing processes. The next phase involves affixing security features. Hologram stripe reels are laminated onto the paper using heat and pressure. These stripes contain microtext, dynamic color shifting effects, and complex holographic images that are difficult to replicate. The prepared reels are then subjected to visual inspection using high-resolution sensors and human oversight to identify any inconsistencies or defects. After inspection, the paper is moved to the printing section. The first step is automatic packaging and loading of the paper reels into the printing units. The printing process starts with offset printing, which applies the base background design in multiple colors, simultaneously using metal plates. This is followed by silkscreen printing, where the signature emerald number, a large value numeral with color shifting properties, is printed. This element changes shade from emerald green to deep blue depending on the viewing angle. The third stage of printing is intaglio, a high-pressure technique that creates raised tactile features on the surface of the note, such as the portrait, numerals, and architectural motifs. Intaglio not only enhances security, but also helps the visually impaired identify banknotes by touch. After each printing step, sheets are subjected to quality control, where advanced camera systems and trained operators verify alignment, ink quality, and the presence of all security features. Once printing is complete, the large sheets containing multiple banknotes are transferred to automatic cutting machines, which slice them with high precision into individual notes. These are then stacked, counted, and packed into secure bundles using automated packaging systems that wrap and label the currency for distribution. Each batch is traceable through barcoding and logged into a central system for inventory control and authentication. Throughout the process, from cotton bale to finished banknote, every stage is tightly controlled under high security conditions to prevent counterfeiting and maintain the integrity of the currency. The production of the €50 note exemplifies the combination of craftsmanship, material science, automation, and digital verification technologies required to produce a secure and durable medium of exchange for the European economy. The entire workflow involves close cooperation among paper mills, security specialists, printing technicians, and national central banks, ensuring not only aesthetic consistency, but also compliance with stringent standards across the Eurozone. The final delivery process includes secure transportation to central banks and controlled release into circulation, completing the journey of a highly engineered product. Every production stage is documented and audited to ensure full accountability and traceability from source to user. The MDF production line, with a continuous press capacity of 1,000 cubic meters per day, is a sophisticated, fully automated system designed to convert raw wood logs into high-quality MDF boards through a series of precisely coordinated processes. The production begins with the log feeding conveyor, which systematically transports debarked logs into the processing line. These logs are fed into the drum chipper, a high-capacity machine equipped with rotating blades that reduce the logs into uniform wood chips, typically 20 to 30 millimeters in length, ideal for fiber production. The chips are then transported by the chips conveyor and chips chain conveyor, which use a series of belts and chains to move the chips efficiently to the chips silo. The chips discharge screw, located at the silo's base, controls the release of chips onto the chips belt conveyor, which delivers them to the refiner. In the refiner, the wood chips undergo mechanical and thermal processing. High-pressure steam softens the chips, and rotating discs grind them into fine wood fibers. During this stage, resin and wax are injected to enhance the board's strength and moisture resistance. The resulting fiber resin mixture is dried to a precise moisture content and transferred to the fiber forming machine. This machine uses air streams to evenly distribute the fibers into a continuous mat of uniform thickness and density. The mat scale weighs the mat to ensure it meets weight specifications, while the moisture meter monitors the mat's moisture content, typically maintained at 8 to 10%, to optimize pressing conditions. Before entering the press, the mat passes through a permanent magnet, which removes ferrous contaminants such as nails or metal fragments. The pre-press then compacts the mat, reducing its thickness by up to 50% and improving density uniformity for the final pressing stage. The edge trimming saw cuts the mat's edges to achieve the desired width, ensuring clean, straight edges. A metal detector scans the mat for any remaining non-ferrous metal impurities, safeguarding the press from damage. The prepared mat then enters the continuous press, a critical component driven by the driving system, which ensures smooth, uninterrupted movement. The hydraulic system applies precise pressure, typically ranging from 150 to 200 bars, while the thermal oil secondary circulation system maintains consistent temperatures, around 180 to 200 degrees Celsius, to cure the resin and form a solid MDF board. During pressing, the online density meter continuously monitors the board's density, ensuring it meets the target range of 600 to 800 kilograms per cubic meter. If defects are detected, such as low-density areas, the affected sections are diverted to the rejection nose conveyor and sent to the recycle screw, where they are broken down and reintroduced into the fiber preparation stage. The pressed board exits the press as a continuous sheet and is cut into precise lengths by the diagonal saw, typically producing boards 4 to 6 meters long. The thickness and blister meter inspects the board for surface imperfections, such as blisters or thickness variations. The boards are then cooled in the star cooler, a rotating cooling system that reduces their temperature to below 50 degrees Celsius to prevent warping and stabilize their structure. After cooling, the boards are transported by the belt conveyor with scale, which weighs each board to track production output and verify quality. Substandard boards are diverted to the waste board receiver for recycling or disposal, while accepted boards proceed to the stacking conveyor and are organized by the stacker into neat piles for further processing. The sanding process begins with the feeding hydraulic lifter, which positions the boards onto the rotary roller table. The board pusher and alignment roller ensure precise alignment before sanding. The boards pass through a 2-head sander and a 4-head sander, which use coarse and medium grit belts to remove surface irregularities and achieve a smooth finish. The finishing sander and polishing machine apply fine grit sanding and polishing to produce a surface suitable for coating, lamination. After sanding, the boards are transported to the cutting section via the swing booking station and booking station, which align and group them for cutting. The longitudinal servo feeder precisely positions the boards for the longitudinal book saw, which cuts them to the desired length. The longitudinal discharger moves the cut boards to the transversal servo feeder, which aligns them for the transversal book saw to cut to the required width. The transversal discharger transfers the finished boards to the stacking system, where they are neatly stacked. Finally, the satellite trolley transports the stacked boards to storage or shipping areas, completing the production cycle. This highly synchronized process Leveraging advanced automation and real-time monitoring ensures the efficient production of high-quality MDF boards with minimal waste, meeting the 1,000 cubic meter per day capacity.